Um, People did not work very efficiently in class, so I'm pretty worried about your test, partly because you should be putting forth effort. That's what people do if they want to be successful. So I would expect these type of problems to be ones similar to things you should be able to do in class on your test. This one, essentially, it's like determine the work done. So the work is the change in energy. So this is a change in gravitational potential energy. So they lift this 300 kilogram mass to a height of 0.9 meters above the ground. It's mgh. You could use either 9.8 or 10. I decided to use 10 for these to make my life easier. So that's about 2,700 joules of energy of work that's done. This one, hands full. Basically pulling a rope to drag the backpack, pulls up and rightward. So again, I drew a diagram, which I like to do. Force of 22.9 newtons. Pulled at a horizontal distance of 129 meters. You're asked to determine the amount of work. So work is basically force multiplied by the displacement in the direction of motion. So I'm only interested in the component of force that's acting horizontally here. So that's a trig thing. We've done trig before this year. You should know how to do that in your calculators. So force, distance, cosine of 35 degrees, that gives me about 660 joules. This one, it's a lab where you could run up and down stairs, trying to change your kinetic energy, or your potential energy. So this person's going to lift their body by 2.29 vertical meters. So the work is essentially going to be the change in gravitational potential energy, very similar to this problem. So essentially you could do mgh. So that gravitational potential energy is the same as the work done, which is force distance. So 102 times 10 times 2.29 meters vertically. So that gets me a total of 2,335-ish joules. And then watts is that divided by the amount of time. So that comes out to 1,770 watts. 1 watt is 1 joule per second. So this one, again, they've got something, a cart, it's moving at initial speed, going to be moving up. So it has initial energy and final energy. So you've got kinetic energy plus potential energy initially equals kinetic energy plus potential energy at the end. So 1/2 mv squared plus mgh equals 1/2 mv squared plus mgh. I don't know why I swap these, but whatever. So that ended up being 4.01 joules you had initially. At the end, you have 3.4 joules of potential energy, so whatever's left is kinetic energy, and you can solve for that 1.1 meter per second. This one, this is way easier to solve than if you use kinematics formulas, which are motion formulas. So you think the initial and the final energy. Initially, it's moving. The pitcher threw it straight up. 45 meters per second. Gravity slows it down at an accelerated rate of 10 meters per second every second. So you can figure out the height that way. So 1/2 mv squared equals mgh. Mass, it doesn't matter what the mass of the baseball is because it'd be the same on each side of the equation. So I just left it as the letter M, and it cancels out. So I get around 102 meters. That's over a football field in height that he could have thrown it vertically, which is pretty amazing. For these ones, which it seems like people decided they didn't need to do, these are really good problems. So you're looking at kinetic energy, potential energy, and then the total mechanical energy, which is the total added together. At the end, all the energy is kinetic. So if you're right before they hit the water, if all that mechanical energy is kinetic, then you can figure out the speed that way. So it's 146 meters per second. Fortunately, there normally is a parachute, right? This is a pretty good one. Top Thrill Dragster, which I think they have stopped this year because I had so many mechanical problems, which is probably not a bad idea. At any rate, so the kinetic energy before the acceleration was 0, not moving at all. The kinetic energy just afterwards, I think I might have gotten this a little off. I used 53.9 instead of 53.6. So my answers may be a little bit off from yours. So that's around 1.48, around 1.5 times 10 to the 5th joules. So in this case, then, we convert feet to meters because it gives you the conversion there. The potential energy at the top, which is 128 meters up, would be 130-ish thousand joules. So then the kinetic energy at the top, the motion should be 17,600 joules. In reality, it's going to be 0 if it's at the tippy top. So what that means is that's probably the amount lost due to friction. But for this problem, that makes sense. And it's just then asking you to determine the speed at the top if that was the kinetic energy. So hopefully those help. Again, you got a test coming up this Friday.